All right, let's talk about one of the absolute cornerstones of software design, the solid principles. But look, we're not just going to go through some dry definitions here. We're going to get inside the head of a senior developer and really understand the one big problem these principles are trying to solve: how to write code that doesn't fall apart the second the world changes.
So let me ask you something. Where do most software bugs really come from? Seriously, think about it. If your mind goes to things like typos or a simple syntax error, well, that's just the tip of the iceberg. The real, deep-down problems, the kind that make a code base feel brittle and terrifying to touch, they come from somewhere else entirely.
I can tell you, after decades of building software, this is the one truth that just keeps proving itself over and over. Most bugs, the expensive ones, the ones that take down production, they don't come from a misplaced semicolon. They come from bad design. Because when a system is designed poorly, every single change, no matter how small, becomes a huge risk. It's like walking through a minefield. And that brittleness, that's a design failure. It's exactly what Solid is designed to prevent.
And that really gets to the core of it, doesn't it? Solid isn't about being clever or writing some kind of perfect academic code. Now, it's a super practical philosophy. The goal is dead simple. Make any future changes to your software cheap and safe. If you find yourself scared to touch a piece of code because you don't know what might break, that's a huge red flag that one of these principles was probably violated.
Okay, let's dive in, starting with the first letter, S. This stands for the Single Responsibility Principle. And you know what? It's probably the most famous of the 5, but it's also, by far, the most misunderstood.
And this slide just nails the difference. The beginner mistake is thinking SRP means one class, one task, or one class, one method. That's a recipe for disaster. You end up with thousands of tiny, meaningless classes. The senior-level reality is much more powerful. A class should have only one reason to change, and that reason is tied to an actor, a person or a group. Think about it. The finance department is an actor. The marketing team is an actor. The database administrators are an actor. A class should only serve one of them.
Here's a textbook violation we've all seen, or probably written: an order service class. On the surface, it seems logical, but let's break it down. Who cares about the business rules for placing an order? The business analysts. Who cares about the email template? The marketing team. Who cares about the database schema? The DBAs. And who cares about the PDF invoice layout? The finance department. You see, 4 different actors, 4 different reasons for this class to change, all mashed together into one fragile piece of code.
So the fix is to tear it apart based on those reasons to change. The order service now only knows about the core business logic. The order repository only knows how to talk to the database. The notification service only knows how to send emails, and the invoice generator only knows about PDFs. Boom! Just like that, a change to the invoice layout has a 0% chance of breaking the database logic. Each piece is safely isolated.
All right, next up are O and L. Now, I'm grouping the open/closed principle and the Liskov substitution principle together for a reason. They're both about the same high-level goal: helping you build code that you can add new features to without breaking all the old stuff that's already working.
The open/closed principle. It sounds a little bit like a riddle, right? Open for extension, but closed for modification. But the idea is actually super powerful. It means you should be able to add new functionality to your system without ever having to go back and change existing, tested, proven code.
And this right here is the classic OCP violation. It's where so many systems start to rot, this giant if-else-if block. It starts small, maybe just with credit cards. Then the business says, we need PayPal, so you add an else if. Then, we need crypto, so you add another. Every single time, you're modifying the core of this logic, retesting everything, and praying you didn't introduce a regression bug. It's not scalable, and it's incredibly risky.
The pro move is to get rid of that if-else chain entirely and use polymorphism. You create one payment method contract, an interface. Then, you create a new class for each type: card payment, PayPal payment, and so on. Now, when the business wants to add a new payment method, you just add a new class. You don't touch the old code at all. That's it. Zero modification. That's the principle in action, and it's beautiful.
Okay, next up is the Liskov substitution principle, or LSP. Now, this one is a bit more subtle, but man, is it critical. Breaking it is what causes those completely baffling production failures that are impossible to find. The core idea is that inheritance is more than just sharing code. It's a behavioral promise. A child class can't just have the same methods as its parent. It has to behave in a way that anyone using the parent would expect. No surprises.
And here is the perfect example that makes it all click. So you have a bird class, and it has a fly method. Makes sense. And a penguin, well, a penguin is a bird, right? So you have it inherit from bird. But wait, penguins can't fly. So what do you do in the fly method? Maybe you throw an exception. The code compiles, everything looks fine, but then at runtime, some piece of your code gets a list of birds and says, okay, everyone, fly. And the whole application crashes. The penguin class broke the promise. It surprised the caller.
The fix is a fundamental shift in thinking. You have to stop modeling your code based on what something is in the real world and start modeling it based on what it can do. So instead of one bird class, maybe you have a general bird interface and then a more specific flying bird interface. Now, only the classes that can actually fly will implement flying bird and get that fly method. No more surprises, no more runtime crashes.
All right, let's bring it home with the last two principles, I and D. These two are all about managing the connections between your classes to create clean, decoupled, and flexible architectures. This is where we really get into building systems that are a joy to work with.
This leads us right into the Interface Segregation Principle, or ISP. And this quote says it all. Interfaces are contracts, not just a random bucket for methods. When you create one massive, fat interface, you force every class that uses it to know about a bunch of methods it will never, ever need. It creates this unnecessary coupling that makes your code fragile. A change to one method you don't even use can force you to recompile and retest your class. It's crazy.
The solution is wonderfully simple. Just make your interfaces smaller and more focused on specific roles. Instead of one giant worker interface that has work and eat methods, you split it. You create a workable interface and an eatable interface. Now a human class can implement both, but a robot class can just implement workable without being forced to have a nonsensical eat method. Clients only depend on the exact methods they need, nothing more.
And finally, we arrive at the Dependency Inversion Principle, or DIP. And honestly, this might be the most important principle of all for building modern applications. The core idea is this. Your important high-level business logic should never, ever depend on low-level implementation details, like a specific database or a certain third-party API. Instead, both should depend on abstractions, on interfaces.
Here's what that looks like in the real world. Instead of your order service having a line of code that says new MySQL order repository dot, which hardcodes it to MySQL forever, it should only know about an abstract order repository interface. Then you let a framework or dependency injection container handle providing the actual MySQL implementation at runtime. This inversion of control is a game changer. It makes your business logic totally independent of the database, which means it's incredibly easy to test and ridiculously easy to swap out later.
So we've walked through all 5 principles one by one. But the real aha moment comes when you stop seeing them as 5 separate, disconnected rules and start seeing them as one single, unified mindset that has a very clear goal.
Let's just tie it all together. Look at this. Solid is really just a defensive strategy to protect your most valuable code from different types of change. SRP protects you from the ripple effect, where one small change breaks 10 other things. OCP protects you from the chaos that comes with adding new features. LSP protects you from those nasty runtime surprises. ISP protects you from depending on things you don't need. And DIP protects you from being locked into a specific database or framework. It's all about building walls to insulate your core logic.
But, and this is super important senior-level wisdom, don't go crazy. Solid is for code that needs to live a long time and evolve. If you're writing a 5-line script, a throwaway prototype, or a super early startup MVP, where the only thing that matters is speed, trying to apply all these principles perfectly is just over-engineering. You have to know when to use the right tool for the job. Context is everything. So if you ever need that one perfect sentence to explain this whole philosophy, the interview gold answer, this is it right here. Solid is all about making change cheaper and safer. And it does that by isolating who is responsible for what, by depending on stable contracts instead of unstable details, and by making sure our code behaves the way it promises to behave.
And that's the final thought I want to leave you with. Anybody can hack together code that works today for this one specific set of requirements. The true mark of a professional, of a senior engineer, is writing code that continues to work and is easy to change for years to come. That is the real, lasting value of building with a solid mindset.